So far, we have discussed X-ray reflectivity and GID. Both techniques actually use the fact X-ray scatters from electrons. So what do we get actually is electron distribution. But we cannot tell these electrons from which element, so they are not element sensitive. The technique I'm going to talk about is element sensitive. This is X-ray fluorescence near total reflection, or you can simply call that XFNPR. With this technique, we can direct probes to specific element at the interface. Here's the outline or a list of questions I hope I can explain well in this talk. These questions are: what's the X-ray fluorescence, and why it's useful, and why I want to do that near to the reflection or near to the critical angle, and what can we learn from this technique? Okay, let's start with the first question. What is X-ray fluorescence? When X-ray strikes on the liquid interface, we can get a reflected beam, or sometimes we can get diffraction peaks if there's long range ordering there. But let's see what happens if we take a close look on atomic level. Here's what it is. We have the nucleus in the middle. I use the sulfur atom as example here. The nucleus in the middle, it has protons and neutrons. And outside nucleus, there are some electrons moving around different orbits or shells. And inner shell has lower energy, and outer shell has high energy. So when X-ray comes in with high enough energy to lock out electrons from inner shell, it leaves an empty spot here in the inner shell. And we know electrons from outside, from out shells, they have high energy, so they like to fill in this empty spot. And during this process, it will release energy because shells have high energy here. And sometimes this energy is released as a form of creating a new photon or X-ray. And this X-ray has energy exactly equal to the energy difference between these two shells. And we call this phenomenon as X-ray fluorescence. So X-ray fluorescence is the emission of X-ray from excited atom, is a byproduct of electrons from out shells falling to the inner shells. Okay, so why is it useful? Here I show the electron shells by straight horizontal lines instead of circles from the previous slide. So the bottom lines have low energy, top lines have high energy. We also have a bunch of vertical lines. Each vertical line represents a path of electrons falling from one shell to the other shell. And we know this process will create X-ray fluorescence. So we call this line as X-ray fluorescence emission line. So one element can have many emission lines. And this picture shows how we name all these emission lines. For example, like K alpha 1 here, this is an electron from L3 shell to K1 shell. And I got this picture from this website. This is a very useful online tool for X-ray. And we're going to go to this website a few times today. So each electron has shells with characteristic energies. So the energy from emission line from different elements are also different, as shown in this table here. For all the elements I list here, their emission lines are all different. So the X-ray fluorescence emission line is kind of like a fingerprint or ID for any element, and it's going to be very useful. And here is an example. Here is a fluorescence spectrum from a multi-element sample. As you can see, you can easily identify all these elements by just knowing their emission line energies. So this technique is element sensitive, and also really only need a very small amount of material to create any decent fluorescence signal. So this technique is also sensitive to the trace amount of material. Okay, now let's go to the third question. Why want to do that? We're not there yet. Okay. So the third question here is how to measure X-ray fluorescence spectrum. Like the spectrum we show you in the previous slide. It's different from X-ray reflectivity or GID, where we only need to measure the photon count at a specific energy, which is the incident beam X-ray energy. But here we need to measure the count for every different energies. For that, we need a special detector we call the energy dispersive detector. And here I give an example here. The most important part of this detector is the silicon multi-cathode chip. It has anode in the middle and a multi-cathode around. And this design creates a drift field that will drag all the free electrons to the anode. Okay. Let's say X-ray, when X-ray hits this silicon chip, it create electron hole pair. High energy X-ray will create more electrons. And these electrons will be connected by an anode and create a charge pulse. And with some electronics, we can convert the charge pulse to the voltage pulse. Of course, the voltage is proportional to the X-ray energy. But with more and more X-ray coming, we get more pulses with different energy, with different voltages. And we can sort them out, we get counts, both channel. So the channel is kind of proportional to the voltage. So now we need to convert channel to the X-ray energy. For that, we need to detect the calibration. Usually we use a radiation source, which generates X-ray with the energy we know. One of the most common radiation sources we use here is iron-55. Iron-55 is a radioactive isotope of iron. And it can decay to manganese-55 and also at the same time create an X-ray. And we call this process as electron capture. Here is a typical spectrum of iron-55. It has two emission lines. And on the right side, I show you the emission line from iron and also surrounding elements. As you can see, we have three columns here because we have three lines here, K alpha 1, K alpha 2, and K beta 1. But if you look at carefully, for example, for iron, K alpha emission line and K beta emission line are very close. They are only separated by 13 electron volts. And the energy resolution for our detector is about 150 eV. So this difference is way smaller than our energy resolution. So the first peak you saw here is actually the combination of K alpha 1 and K alpha 2. And we usually call that just K alpha. The second peak is K beta 1. So now the question is this really the fluorescence from iron? Actually, the answer is no. Okay, let's look at this electron capture process. So we have nucleus iron-55, and it can capture one of the electrons from the inner shell to decay to manganese-55. At the same time, they leave an empty spot in the inner shell. So after that, the fluorescence process happens. So this fluorescence actually is not from iron, it's from manganese. So instead of iron, these two emission lines are from manganese. So we can convert them from channel to energy. Okay, so now we can talk about the third question. Why I want to do that around the critical angle of QC? Before we talk about that, we need to mention the X-ray penetration depths. And Mark already mentioned that yesterday. So X-ray intensity decays when the penetrates deep into the surface. So it's proportional to this exponential decay, is e to the minus z over lambda. Lambda is X-ray penetration depth. It's determined by three factors: X-ray energy. So of course, X-ray with high energy will penetrate deeper. Incident angle. X-ray with high incident angle will penetrate deep. And also material. X-ray can penetrate deeper into light material compared to heavy material. And we do have a full equation for the penetration depth. It's a little bit complicated. Here, the K0 is a wave vector. We already talked about it yesterday. And it's determined by X-ray energy. Alpha is the incident angle. And beta, if you still remember, that's imaginary part of reflective index. And that's determined by X-ray energy and material. So with this equation, we can plot X-ray penetration depth from water-air interface as a function of the QZ for different energies. This equation looks complicated, but we can simplify that as under some extreme conditions. One extreme condition is when alpha is much smaller than alpha C, and the penetration depth equals 1 over QC. The other condition where the alpha is much larger than alpha C, and penetration depth equals D times sine alpha. D is the attenuation length. So basically at a large angle, penetration depth is attenuation projection along Z direction. Or you can look at it this way, penetration depth accounts for the intensity decay along Z direction, which is normal to the interface. And attenuation accounts for intensity decay along the beam direction. Okay. At an extreme case, when the incident angle is 90 degrees, these two basically are the same. So the X penetration depth is equal to the attenuation length. Okay, here is the first exercise. Okay, so we have this simplified equation for the penetration depth at different extreme conditions. Here, QC is the critical angle or critical Q for pure water-air interface is 0.0217 volts Armstrong. And we can go to this website to calculate attenuation length for different angle and different energy. For attenuation, we can calculate for different material and different energy. So here, I want to calculate the penetration depths for these two different energies and these two different Q. And I'll give you a couple of equations to help you to convert Q to the incident angle alpha. Okay, now I'm going to leave from my talk for a minute. Let's go to that website. I will show you how to get the attenuation length from that website. I'm going to stop sharing here. Oh, it's just new share. I have to stop sharing. Okay, here's the website. You can easily just type that link to your web browser, or maybe you can just open a new one, just simply type LBL X-ray and search that, and the first thing come out is that website link. And this is the front page, has a bunch of useful things like atomic scattering factor, index of reflections, which you might need that later on today. And the thing we want here is attenuation length. But before we go to that link, I want to show you the link at the bottom is X-ray data booklet. If you click this button, okay, and if you, there are also a bunch of useful things here. Let's focus on X-ray emission, X-ray energy emission energies. So you can see this plot. I got this figure from this website that shows you how we define all the emission lines. And if you go to this PDF file, you can see all the emission lines for all the different elements here. Okay, let's go back to the front page. Let's click this attenuation length. First thing you need to put there is the chemical formula. Let's say for the water, we can just put H2O here. But then you have to put the mass density for this chemical. So for water, we know it's 1 gram per centimeter cube, and you have to put your photon energies. So let's say we had 8 keV. So this is in the unit of EV. So you put 8,000 here. The other energy we have is 16.2 keV. So then we only need 10 steps. We don't need so many data, just 10 steps. So you can click the submit request. Then you pop out the new window, just click the data file here. Okay, that's the result. So this is water and density is 1. The first column is the photon energy. The second column is attenuation length in the unit of the macrons.